such as C, C++, Java. So hoping that you're all coming armed with that. So I'm going to proceed with that assumption. A little bit about the course materials. First of all, people remote. If for any reason you're not seeing something that I'm doing here, please let me or Bill, who's in the other room, he's here to help us out. You can either send us a chat message, and Bill will alert me to that chat message if I don't notice it myself, or you can just go ahead and raise your voice and let me know what's going on, and I'll try to help you out. I have a laptop set up here where I'm displaying some of the material, and I've got the desktop, so they might not be in sync. So just keep me posted if there's anything going wrong or something you don't understand. I don't use PowerPoint slides for this. I use something that's called a TiddlyWiki. This is something that you could completely modify while we're taking the course if you wanted. You're welcome to make notes right in it. If you haven't opened it up already, there should be an HTML file. And Bill, if there's any trouble, anybody opening up the TiddlyWiki, let me know. Does everybody here have this open? Okay. And does everybody have bomb.exe? All right. If you have any trouble, let me know. But I'll assume you've got it open now. So on the TiddlyWiki, you can just click Edit or double-click any one of these items, and it will bring up what looks like some wiki language. If you do this on accident, you can just hit Done or Cancel. Done will save changes, Cancel will erase them. There are some points through the code where I've actually masked stuff away, because I actually, when Zeno and I designed these materials, we said we want this to be something that you can do on your own if for some reason you don't have access to the classroom or whatever. So I have actual walkthroughs for each of the labs we're going to go through. This is a very lab-intensive course, and actually sometimes we're going to start out with the lab and then try to understand what we were seeing afterwards. So I might not talk to the material until after the lab, see as we go along. But this information is going to be commented out. You'll see if you open this up, in some situations we've got these comment marks. If you delete those, it will expose that content to the wiki once you save it. So I don't think we'll be having to worry about that since you're all here with me. But if you have any questions about that, let me know. Where to begin? So, reverse engineering. How many of you actually do reverse engineering on a daily basis? All right, so some of you do this already. So some of this material might be old hat to you, but how about Charles? Matt, I'm sorry.
No problem. I'm one of the weird people that go by my building.
No problem, no problem. What's one thing that you do reverse engineering for? What's your goal?
I do a lot of work with trying to understand the Windows kernel. So
okay.
I do a lot of Windows bugs.
Okay, so what is the end goal of your reverse engineering?
Try to figure out good states for Windows kernel. Well, basically the project is to try to secure Windows kernel.
Okay, so we're securing things. Okay, so maybe we're trying to do some debugging, or we're trying to find some weaknesses in code, or malware analysis. We're trying to understand something so that we can get it out of our system or figure out how to interact with it. Of course, there are other nefarious purposes. I am no legal expert. I'm not going to tell you what you can use reverse engineering for. You are more than welcome to hack at the bomb.exe, which we're going to be coming across pretty soon here. But when you get started with reverse engineering, you got an application, you want to understand something about it. First, you want to ask yourself, what is it I'm looking for? And it's very easy to get lost in the weeds. There's so much to look at, so many different functions. There's a lot of stuff that might just throw you off the trail. Always remember what it is that you're looking for. So, are we trying to understand, how this thing communicates? Do we know something about where our program crashed? If you know some output string that appears on the screen when your program crashes, maybe you want to start looking for that. Start with that. Have some sort of focus. So what are the outputs? What are the inputs? And what behavior do we already know about this thing? So you might have already done you might have executed the thing to try to understand what does it do. And a little bit deeper dive. So what are we looking for? We're looking for maybe some strings of interest. We're looking for particular functions. Maybe you know that it talks on the network, so we're looking for some sort of Windows API call that says send or receive. And maybe we're looking for some sort of iterative behavior. Maybe we know that it does something over and over again, so we're looking for some sort of loops or conditional statements. So our tool of the trade is IDA Pro today. There might be other tools out there that you use. We are going to focus on IDA. This course is about static analysis. Okay, we might do a little bit of debugging over the course of day 2, but today is going to be all static analysis. You may find that in some of the exercises, the work that you're doing is aided by actually running the thing while trying to look at the code. I won't stop you from doing that. Whatever gets you to the result we're looking for, that's cool. But let's go ahead and actually open up IDA. So, everybody find IDA in order to get it? Okay. Now, typically when I use IDA, I have IDA on my desktop, I drag the executable on top of it, or I do something like this. Open up IDA and click Go. And we just have blank canvas, and we need to actually load up our file. So, we're missing something. Yep. Okay. So we're going to go ahead and drag bomb.exe into IDA. Let go. It's going to bring up this load a new file dialog, and I'll give these guys a second, see if they can straighten out their problem here.
Are there any other programs that are necessary too, that what I'm forgetting?
No, this should be pretty much it. I mean, I asked to have Python installed, so some of these problems you'll be able to solve through writing little scripts. I encourage you, by all means, if that helps you, go ahead and do it. I personally use Python for these purposes because it is kind of the de facto language that's used in a lot of the tools. IDA actually has a Python SDK, and as well as one that's written in C. And there are various other tools that you might want to use Python for. So, Mike, do you think this is probably going to be a while?
No, it's all done. It was just the system restore that was weird. It did Windows updates over the weekend.
But IDA's.
Yeah.
Okay. So once we got IDA open, load a new file. Okay. So just drag bomb.exe onto the IDA desktop there.
Yeah.
All right. And we're going to click OK. But before we do that, I'm just going to talk about this a little bit. So typically, don't do a whole lot with this guy. This allows you to tell IDA where some of the information in the executable is. This is something that you're typically going to do when somebody's trying to divert you or trying to make it difficult for you to understand where everything is. Or let's say you have a malicious doc file, and you know it has shell scripts in it. You want to open it up in IDA. IDA doesn't understand doc. It's not going to point you in the right direction of where the shell code is, obviously. So you might do something in here to tell IDA where to find the code. But we won't worry about this at all today. Later on, we'll look at this load resources option. But now let's just click OK. And you're asked, do you want to load symbols? So when you compile an application, you can choose whether or not to output symbols. Symbols are basically pointers to where functions or variables are located in an executable. All right. So as I was saying, symbols not always provided with an application. In fact, if you have a malicious binary and you have the symbols for it, that's a really just lame attacker. He's probably got much bigger problems than just sharing the symbols with you. So we're going to go ahead and say yes, we would like that symbol information available to us. And got this ugly version of IDA. So newer versions of IDA provide you a much more clean interface. Everything's tiled. We get to deal with the free version today, but you're going to see something a little bit different if you decide to go ahead and use the full-blown IDA. But a lot of these features are kind of the newer versions are backward compatible with what we're doing today. So a lot of this should, if you go ahead and use a registered version of IDA, you should be seeing what we're seeing here. So whenever you open up a new binary, it's an executable file that IDA understands, such as a Windows PE, like this is. You're going to get this information. It's just a bunch of metadata about the file. So we've got the MD5 of the file, so the signature of it, file name format. So this is a portable executable. It's a format that's used to execute programs in Windows. The image base right here is the address in virtual memory of where this application was loaded. So the file that you clicked on, when you double click an exe and it launches, the image base is where in memory that file begins from the first byte of that file. And located at that first byte should be MZ. And that's an indicator that we've got an executable. And we got a bunch of other information. We don't need to go into detail. If you scroll down, you'll see a main function. And so we've got right here, this is our stack. On the stack, you've got variables that you're using throughout the course of the application. You've got functions calling functions. One function wants to pass information to the function it's calling. That information is right here. So these guys right here are arguments that were passed when this function was called. and this is some sort of local variable. So when you got your code, you declare an integer with the name bar_4. That's what this would be. Now, on the right-hand side here, you see these are offsets from the base of the stack. So, do I have any whiteboard that I can here? I guess over here.
If you use a black pen,
So when a function is called, absolutely. Oh,
Might be worse.
well, I'll try to draw. So when a function is called, just before the call. Sorry, remote users, if you can't see this, but the markers are insufficient. So, okay, so let's say we're calling some function.
green is terrible.
So if we're calling a function, let's call it, so in C, you're going to have something like foo, part 1, part 2. Okay. When we call this function, what's going to happen is the calling function is going to have its stack here. We're going to have return address. And then we're going to have local variables. But before this happens, the calling function is responsible for putting arguments onto the stack. So this is what we're seeing here. So I like to draw my stacks one way, Zeno likes to draw his stacks the other way. He always harasses me about this. But this is the way I see it in IDA. So this is the way I draw them. Local variables are up here, so this would be your -4, this would be bar_4.
So you have the bottom of memory at the top.
Right. Yes, I do everything backwards. And this would be 0. And so -4 is a location here. 4, 8. And then we got, so one thing I want to note is that this says bar4, and oftentimes people start to think, well, that must be 4 bytes off from some particular location. Just to be clear, you might see in IDA somewhere that says bar4, but it's actually an offset of C. I suggest that you don't think about this as a number, but just some arbitrary name for the variable. Always take a look at the stack parameters here to get an idea of whether or not the variables offset that number. But we'll come to that later. So in IDA, we're provided these graphs. As you saw, there was just a single block. Okay, that's a very simple function. Not a whole lot happening there. And this was a feature that was added in IDA 5. It's something that For years, people were using OllyDebug, WinBag, WinDebug, GCC, GDB. Sorry, I don't know why it says GCC. And in IDA, they added in version 4.17, they added a graph tool, and it was all right. It allows you to just look at a call graph, and it also allows you to look at the graph of a function. So you've got things connected by branches, you've got things connected by loops, and we'll demonstrate this soon. But you can use IDA in this graph view, which you can see here. We've got a bunch of nodes connected together. These branches here, the red and the green, that's conditional. Green is going to indicate that a jump has been taken, and a red branch says that the jump wasn't taken. That's based on some sort of conditional. So if we zoom in here, we see, what's that keyword shortcut that you just used? Good question. So in order to zoom in IDA, if you hold the control key and use your mouse wheel, you can zoom in and out. So if everybody wants to go ahead and just try that.
That I think applies also everywhere too. So
Right.
So that's one of those universal ones.
Right. So surprisingly, a lot of people, it's new to them. So don't be afraid to ask a question. If there's something that I do and you're wondering how did I do that, please let me know. If for some reason you end up off of the graph, we have this graph view, and if you click on it, it will take you to wherever you click on the graph. So if you lose the graph for some reason, you are just seeing a blank space, just go ahead and use this graph overview, and if that's missing, then raise your hand or send a chat to Bill, and we'll get you straightened out. Okay. So one of the other features IDA has is it's got this context highlighting. And for those of you following along in the wiki, we're on this page here. So context highlighting allows us to understand the flow of any particular variable or any particular register throughout the function. So let's say we click on argc. We want to see where this is used. You can see right at the beginning of our function here, we've got a comparison. So if it's 1, it's going to take this jump on the right, and if it's not, then it's going to go to the left. So compare, when you have a compare instruction, it's going to say set the 0 flag to 1 if this comparison matches. And so we see right here it's doing a JNZ. If it's 0, we're going to jump to the right. And we can see, actually, said that backward. So if the comparison succeeds, we're going to go to the right here and continue on checking our argc. If not, it's going to jump down to this block here. So once again, we see argc is used here. So this context highlighting allows us to understand where is this variable used? Is it important to the function? So you might want to just click on a variable and zoom out far and see where is this thing used. Okay. You can do this with function names. So click on one of these functions, and what do we see here? We see this function is called repeatedly throughout the course of our application. Same thing with printf. So take advantage of that feature to trace any particular information that you're trying to understand. If you're trying to see how variables moved through the registers, you can go ahead and do that with registers as well. So, and push and pop instructions. So you want to see how the stack grows or shrinks. We see all these calls to push. That might help us to understand, where are we at in the stack. You might have a successive bunch of push calls, and then you'll have a call instruction. Okay, that might tell us how many variables are being given to that function. So, for example, right here, we've got a push and then a call. So in this case, we might assume that this only takes one argument. Okay.
Are all parameters passed in the stack?
No, parameters can be passed through registers, and that's something that we'll come to tomorrow. Pretty much everything we're going to deal with today is parameters passed through the stack. And we'll talk about different calling conventions. So when a function's called, the designers of the compiler can decide, or the person who's writing the code can decide how parameters are passed to a function. And so, as he's pointing out, not always going to be on the stack, but today it will be. Okay. So we also have this ability to color instructions. So coloring will give us some sort of indication of, say we're trying to trace some particular function and it gets very convoluted. You can organize your code by coloring. So you can color a block. So let's have everybody try this out. We're going to take this block over here. And you'll see in the upper right-hand corner of this block, we've got a little color grid. So if you click on that color grid, you'll get a color chooser, and you can say we'll choose green. Now maybe we can use it to say we've analyzed this block and we understand it already. Or maybe you could write some sort of a IDA script that goes through, and when you execute a debugger, it colors every block that it visits. That's something that we can discuss outside of class. We won't get into a whole lot of scripting, but if you have any questions about that, let me know. So, anybody having any trouble with coloring? Any questions?
Matthew, can you hear me?
Any questions for the remote users?
If IDA gets confused about control flow because of obfuscation or whatever, can you have it regraph once you point out the error of its ways?
Can you have it regraph? Okay, question was, if IDA gets confused about the flow of the application due to some sort of obfuscation, can you have IDA regraph it? Well, I'm assuming that you're asking if you make some sort of changes.
Yeah, or could the flow be
Can you regraph it?
on something external to the program that's only determined at runtime, so it makes a bad guess?
Okay, so that's something. Basically, so IDA might decide that code is in one particular place and isn't really. This is a topic that maybe we can discuss tomorrow. We'll come to, but if let's say you have some block that for some reason gets undefined. So don't need to follow along with me, but if you have something like this, the code, there's, for some reason, this block here just goes into nothing. There's nothing that follows it, and it's kind of an odd end to a function, because usually you're going to have either a jump, a return, a call to some exit function, something that indicates that we've come to the end of this function. What happens is if we define code here, IDA redraws the graph for you. So when you change how code is defined, then yes, the IDA will actually autocorrect itself for you.
It does.
Okay.
Thank you.
So does that answer your question? Okay. Now, another thing I want you to try is just go ahead and click on one of these boxes and just drag it somewhere. Okay, we can move these things around and arrange them as we see fit. If for some reason you do this on accident or you don't like the changes you've made, you can revert them. So if you right-click on any of this negative space, anywhere where there isn't a block, you can click Layout Graph, and it will redraw it for you. So it will rearrange everything. Okay? So, IDA uses all sorts of different colors to indicate what a particular instruction is, what it means, or there are different colors used within the debugger. So we've got blue, which indicates the current instruction pointer, red, which indicates an enabled breakpoint, green disabled breakpoint, and purple indicates when we're debugging, this is a line where your current, so the instruction pointer is pointing at this line, and you have a breakpoint there. So let's say you run the program and you have it run until it hits a breakpoint. You'll see a purple line. So that indicates that's where you are, and that is your breakpoint. And then yellow is highlighting, as I showed you the context highlighting before. So the reason I point out these colors right now is that if you choose these colors in our color grid here, say we choose this yellow, you now can't use that feature. You can't actually see the context highlighting. So I suggest avoiding these particular colors. There are different blues, greens, reds, purples that you can use that won't conflict. So if you've already set yellow when we were experimenting with the chooser here, I'd suggest clicking on there and going ahead and choosing white as the color. Okay. I was mentioning before different colors for branches. So we've got green says a condition was met. We've got red that says the condition failed. And then we've got loops and regular flows. So a regular flow is just two instructions that are separated by some sort of block delineation. So right here you can see we've got this location 401065. It's got a regular flow. So because this block has a jump to it, this is isolated as a single block. And then you can see there's another instruction that goes into here. So that's just a regular flow, whereas we've got the conditional jump, conditional branch. Okay, and in this we don't have any loops, but but I'll show you right here. Not this function. Okay. So it's kind of hard to tell, but loops are indicated by a slightly thicker blue line. So we've got our regular flow, and then we've got our loop branch here. And if you look in your graph overview here, you'll see we've got a block that goes back into a block at the top. This is an indicator of a loop.
I don't know that our blocks really look like yours. There's no loop in my bomb that I can see.
Okay, so we'll come to that. I'm just showing this for demonstration purposes. How about this? One of the really handy commands that you can use is jump to address. And you can use that using G. So hit the G key. Everybody hit the G key. And we're going to jump to OX. Okay, OX tells us we're talking hex addresses. Okay, hexadecimal. And 401810. Again, that's 401810. So if we click OK, we'll jump to that location. And this is the function where I'm looking at this loop. If you zoom out here, you'll see something similar to what we see in the graph overview. All right. So once again, for zooming, control and mouse wheel. Okay. So now, let's say you've jumped to somewhere and you want to get back to where you were before. If you hit the escape key, it'll take you backwards. So you guys should have gone back to the main function. All right. So, and that brings us to our next point. So navigation. I just talked about going to a particular address. You can also double-click. Double-click will allow you to trace to where a jump is. So if for some reason a jump is off the screen, double-click a jump, it'll bring it to you. So right here you can see I've got this jump instruction. Double-click it, and it's moved down to where that is. So sometimes these jumps might be way down the page, and so you can double-click and it'll bring you to it. You also can click on a function. So we've got all these calls here. A lot of them are to things that are in pink. And this is something I didn't mention when discussing the coloring. So these calls that are in pink, those are indicators of a dynamically linked dynamically linked function. So these are things like printf, for instance, as we have here. You might have file open. You might have some sort of networking functions. These are all things where the developer of the application didn't want to rewrite the kernel, didn't want to rewrite the features to actually create files or all these things. So this has already been done for us, so we reuse these functions. And on top of that, dynamically linked says we're not including this function actually into our binary. So the code for this is located elsewhere. It helps us to save on space, and it helps us to do things in a uniform fashion so that the code is always the same. All right, so if we double-clicked on printf, for instance, it just takes us to this iData section. And iData is import data. It's referenced from the headers, which are located at the very beginning of the executable, and we'll talk about that later. And this is basically just a table of addresses where the function resides. So when Windows loads this application, it then says, okay, where's our library in memory? Okay, let's associate the functions from that library into our application here. We'll store this address here, and every time we make a call, we're going to actually jump to this address that's in the table. Okay. So if you hit escape, that'll bring you back to the main function. And then you can double-click on one of these calls to sub_anything. So these are typically user-defined functions, meaning the developer wrote this code and compiled it. And IDA has no idea what this function was called. When you compile an application, as I mentioned earlier, you can use symbols. And if you load symbols for this particular bomb.exe, you would actually see what the author originally intended these functions to be. But because they're trying to be crafty and make it so you don't understand what's going on, that information isn't included. It also is space saving, so that's the main reason why we don't pass this information along. It's really for optimization. We don't really need it. It's useless once the program is already compiled, unless you're trying to understand the application. So hit escape if you already jumped to that function. Now you know how to navigate to a function. And I guess another handy shortcut key is, say you accidentally hit the escape key, and for some reason the address that you went to isn't readily available to you on the screen here. You can hit Control-Enter, and that will take you forward. So that's all in the wiki, in the navigation, under Getting to Know IDA. Okay, and then we have a bunch of other shortcuts that will come in handy. These ones are really just for reference. Okay, we won't have to deal with defining code and defining strings and that sort of thing until later on in the course. But if you are trying to figure out how to define any particular thing, come back to this. And so undefined bytes says, I don't really understand what this thing is. I want IDA to stop telling me what it thinks it is. Define code, so say you come across something that looks like an instruction, you press C, you're gonna see what IDA thinks the code will look like. And P will define a function, and so on. So one of the most useful ones to you is going to be A, which defines an ASCII string, and we'll come across that later on. So once we come across a function that we're actually interested in looking at, the question is then, where do we go? So actually, any questions, Bill, from anybody out there?
None that I've seen in the chat.
Okay, so the first thing we're going to ask is, when we come into this function, what does it do? Does it call a bunch of other functions, or is all the work that needs to be done, all the math, all the logic, is it all contained within the blocks of code that we see? So you might have no calls, and that's going to indicate that this is a leaf node. It's the end of the tree. The thing is the final place where all the logic is done. It might be a function to add two numbers, might be a function to calculate pi, whatever the case may be. Or it might not have any calls because it uses some other mechanism to get to another function, and we'll come across that later on. One example would be interrupts. So interrupts are commonly used on Unix platforms to go to whatever system call that you're interested in doing. So say you want to write a file, you might see an interrupt instead of a call. So regular function is a non-library function. That's the kind of function I was talking about before. This is probably compiled by the user, or it might be some sort of statically linked library that IDA has never seen before. So IDA uses what's called flirt signatures. So if a function is compiled statically, inserted into the application statically, as opposed to having it in some other file, IDA will show you this function and use a flirt signature. It just checks a sequence of bytes, and the whole purpose is to identify functions that we've already analyzed. So we won't get to how to create flirt signatures, but we can do that offline if you want. But IDA provides you a lot of these for standard operating system functions. We've got library functions, and these are the sorts of things like I was showing you. There's the calls to printf. They're the items that are statically linked. They'll have a blue name, but they'll be something recognizable like printf. And then there are the dynamically linked ones, which will be labeled pink. So light blue for the statically linked, pink means they're imported dynamically. So the code for dynamic functions, once again, not in the binary itself. So when you come across these library functions, there's information out there for us, so we don't have to analyze the thing. We don't have to do any work beyond going to, say, MSDN. So MSDN is one of the best resources when you're analyzing a binary. Have that handy. C++.com might tell you things about functions like fopen, printf, these sorts of things that are standard to non-Microsoft applications. And then we've got indirect calls. So you might see some sort of a call brackets EAX. So this says whatever address is in EAX, go to that location, get the value there, get a 4-byte value, or 8-byte if we're in 64-bit, and go to that address. These tend to be very interesting when you're looking at something like a malicious code, or when you're analyzing analyzing a vulnerability or that sort of thing. Because these are the kinds of things that you're going to have to fill in. These are the gaps that you're going to have to fill in. What does this thing do? Where is it going? And sometimes it's on purpose that they're trying to mislead you or try to prevent you from understanding where they're going, and sometimes it's just how the code is built. So what are the outputs? So EAX is the common return register. It's not always the case, but in most cases, EAX is going to contain the return value. And if there's a float, then EDX and EAX is used to return the entirety of the float. So when you're looking at the end of a function, you're trying to understand what is its return value, you can kind of work backwards. Okay, varc is going to be what we're returning from this function. So how is varc used? And this is where context highlighting comes in handy. So we might work backwards to understand what this function does. We see, okay, EAX gets varc. Let's trace the function and figure out what that does. All right. Is there any are there any file system calls? Are there any networking operations? These are the kinds of, other kind of outputs that we tend to forget. So, you know, the output might be, the purpose of the function may be just to write some files. So maybe EAX is completely useless. Maybe it doesn't actually return a value. And then are any arguments written to? So when you have something that's passed into the function, so in our main function here, we've got argc, argb. Look for anything where these are actually being written to. Maybe these arguments are actually passed by reference and somebody wants to change them. Okay. What are the inputs to the functions? We already talked about stack arguments, and as mentioned before, there are other calling conventions. So sometimes registers are used to pass information in. You might also have, once again, you might have file inputs, network inputs. What about the flow of this function? Does it have loops? Does it have conditional branches? Use data overview. You can move around to see, you know, what is the flow of this application. This one doesn't do anything iteratively. Okay. And say you're using IDO in conjunction with a debugger, then this will help you to understand, well, this isn't the behavior I'm looking for because I'm expecting it to do something over and over again. Now we've got these other kinds of flows. So some things that you might see when somebody's trying to mask their code, you might see these calls to $+5. So sometimes people want to save an address in the instructions themselves. Okay, so what they'll do is they'll do this call, $+5. So that's going to just go directly to the next instruction because a call is generally 5 bytes. Okay, so it's $ is just saying the current address +5. So what might happen next is the next instruction is a pop instruction. A pop instruction will take the value at the top of the stack and put it into some register. So when this call occurs, it's going to push the current address and then go to the next instruction. Then the pop happens, and that address of the call instruction is going to now be in some sort of variable or in a register. So that might be a situation where code wants to overwrite itself. Okay, so you have this, it's storing some location where later on it's going to overwrite it, whether it's to get the code out of your site, so when you're debugging it's complicated to understand the flow of things, or it might be just trying to use as little amount of memory as possible to avoid stepping on something that will crash the application. Then we've got indirect jumps. These jumps where just like the indirect calls I was showing before, it's gonna jump some address stored in a register or at a memory location. So just a refresher, when you see something in brackets, that is dereferencing a register or a memory location. So it's going to that register or to the memory address. It's getting an address out of there. It's then going to that address and getting the information added. Then we've got interrupts. And interrupts, well, they interrupt the flow of the application. They say, okay, operating system, there's something I want to do and only you can do it. So int3 is a common one. That's actually a breakpoint instruction. So let's say that you're messing around with this thing and you want it to stop in a particular location. Well, IDA provides you the ability to use hardware and software breakpoints, but you could also modify the binary. So let's say you have an application and it calls to some other application. Maybe it dumps a file and then executes it. If you can intervene between the dumping of the file and the execution of it, you can insert one of these three instructions if you know where the new file is going to start executing from, and then you can get your debugger to break on that. So that's something that we can discuss later, but probably we won't do in this course. But so is there any exception handling? And this is something that's kind of changing. A lot of malware did this in the past, as well as your run-of-the-mill applications. FS0 is a special location for Windows, and it's where the address is located, where a exception handler structure is located. So let's say that you want, when a divide by 0 occurs, or some unhandled exception occurs, you want your own code to execute. So you can replace the exception handler this way. And this is the unhandled exception handler. It's located at FS0, meaning anything that the developer decided that they're not going to deal with. So maybe they'll deal with divide by 0, but maybe they won't deal with access of memory that is for some security-related reason not accessible. So this is something that you may not see as much anymore, but chances are, especially if you're doing malware analysis, you're going to come across this. And then obvious violations. So whether this is on purpose or not, you might have, let's say, you have this EVX XORed together. Anything XORed with itself is 0, and then you see a div. Either somebody really screwed up when they were writing this application, or maybe they're doing this for some particular reason. Maybe they're trying to force an exception.